Okay, I need labs. I don't have a stapler up here. So if it's not, if you can't have to, fold it down. Any more labs? You can. I just go ahead and do it, and I will. Yeah.
Already last time had like 2 lines.
Just fold it in half because I don't have. Oh, what now?
Last time she's coming, but like, and she has like some of the questions.
Okay.
So we should get to class after this.
Yes. Just wait until the end of class. Okay, so let me go ahead and get started. First of all, many of you may be aware I've gone ahead and uploaded the lab grades from the first 2 labs. So I'm finally caught up with grading with the exception of what you just turned in. And I will try to work on that over the next 2 days. I'll pass back labs during lab so that I don't spend the time during class trying to pass back labs. So the only thing I'll pass back during the lecture is going to be exams. Otherwise, I'll pass it back during the lab itself. I will say, and on the very first lab, due to realizing some things needed to change, I went ahead and gave everybody 20 points for the lab portion itself. So your grade is based off, if you didn't make a 25 out of 25, that means that you missed some answers on the quiz for that lab. Whereas the density lab, I did grade. So you'll see that when it comes back to you. So anyhow, I just wanted to let you know what I did with the first lab of the semester. Just as a reminder, you do have an exam on Thursday. It will cover through today's information. So hopefully you've been studying up through today's information so that you can focus your efforts primarily on today's information for the next couple of days. I have not written the exam yet, so I can't tell you a detailed listing. I will say normally in the past, I've done 2 to 3 of each type of electron configuration. I usually have 2 or 3 questions about quantum numbers, 2 or 3 questions related to orbital diagrams. So it gives you a little bit of an idea of how I do different, separate things out. But I usually do it where the electron configurations, which are right or wrong, are roughly 5 points each. So I do try to do that. The Z effective calculations, if you show me your work, you can get partial credit on. But electron configurations, they will be right or they will be wrong. So anyhow, I just wanted to give you a bit of a heads up. Any questions for me before I get started? Yes. Yes, so today during X period in this room, an individual by the name of David Montague will be here. David Montague himself has served on the investigative team that even focused on the JFK assassination. So he's evaluated the JFK files. He has done a lot of other work with the FBI as an investigator. His mother, Ray Montague, is from Pine Bluff, if I recall correctly, and she basically was the hidden figure for the Navy. She was the very first individual to develop a schematic, essentially, of a ship using computers. And they will be in, or he will be in during X period here. Basically, you'll just need to take notes and turn in the notes on Thursday morning for your 5 points of credit. Now he is going to be focusing his talk on the importance of diversity and inclusion and in the STEM workforce, because we all bring together important ideas. And it's all of our ideas are really based off of our backgrounds. So he will be discussing that. I hope to see a lot of you here. Any questions? Other questions? Was that sufficient? Okay. Yes. This Thursday. Other questions? Yes. If you want to eat during the speaker, you'll have to bring your own food. I wasn't able to get orders in time because I didn't have the money. So, other questions? I don't need that. I just need this. Okay, so I'm going to actually start out with doing some more z-effective calculations because those z-effective calculations play into our discussion, which is going to be atomic size and ion size. And atomic size plays into the ionization energies, and ion size plays into ionization energies. So since this is an important point, I am going to be doing some more z-effective calculations. So I'm going to start with potassium. And what I've done is I've drawn the potassium using the Bohr model, though the Bohr model is not accurate. I still went ahead and did so. And you'll notice that the electron I'm trying to find the effective for, I've highlighted in blue. All the other electrons that I will be using in the calculation, I've highlighted in red, so that you can differentiate between those that are part of the calculation and the one that I'm calculating. So basically with this, if I want to calculate the Z effective for that outer electron, that is in the 4s shell, or in the fourth shell. Technically, we don't even need the S, we just need to know that's the fourth shell. So according to our rules, anything that's in a shell lower would be 0.85. So all of these electrons have a weighted average of 0.85 as far as the amount of interference that they provide. According to the rules, for every electron that is 2 shells in or more, they will provide a full 1 as far as the interference that they provide. So all the electrons in the 2s and all the electrons in the 1s, they're going to provide a full 1. So if I were to look at this calculation, my S, which is the shielding constant, it's going to be equal to 8 times 0.85 plus 8, 9, 10, 10 times 1. Which comes out to be 16.8. Now, potassium, to get to the Z effective, that is Z minus S, where Z is the atomic number. Potassium is element number 19. So 19 minus 16.8 is going to be 2.2. Yeah. So this is our Z effective for potassium. Questions? I'm drawing the diagram because I'm hoping with you being able to see it on the diagram, it will help you understand the numbers and what they go to. So let's look at calcium. Let's do that one. Calcium. Again, I've highlighted the electron I'm trying to figure out the Z effective for, and all of the rest of the electrons are in red. Now, because calcium has an electron in the same shell as the electron we want to know, that electron contributes 0.35. Now, every electron within that, one shell in will contribute 0.85. So all the electrons in the 3s and the 3p contribute 0.85 to the shielding of the overall atom. Then we move on to the electrons inside. All the electrons in the 2s and 2p and in the 1s and 1p, 1s, contribute a full 1. So for calcium, our S is going to equal 1 times 0.35 plus 8 times 0.85 plus 10 times 1. So that is a 17.15. So our Z effective, which is equal to the atomic number minus S, is going to be equal to 20 minus 17.15 which is 2.85. So we had a value of 2.2 for potassium. We have a value of 2.85 for calcium. And we could continue and we would wind up with a Z effective for krypton, which is element number 36, of 6.5. Questions about doing the Z effective? So the elements that I just gave you were potassium element number 19, calcium element number 20, and krypton element number 36, all found within the fourth period. What do you notice about their Z effective? Yes. Okay. So Z effective increases from left to right across a period. What does Z effective mean? So basically, Z effective describes how strongly the nucleus pulls on that electron. So Since Z effective increases, that means that the nucleus pulls on those outer electrons more effectively. Since the pull is greater, it means that the atomic size is smaller. From left to right. Across the period. So the atomic size decreases going from left to right across the period. All because the Z effective increases. Again, the atomic size decreases across the period. All because the Z effective increases. Now, folks, if you look back when we were doing elements on Thursday compared to today, you'll notice that the elements in period 4 have a higher Z effective than the elements in the lower periods. So you would think that the atomic size would decrease going down in group 2, but that's not the case. Again, if you look back at what we did on Thursday and compare it to what I just did, you would see that the Z effective for what I just did today is larger numerically than the Z effectives I had pulled together on Thursday of last week. So Z effective doesn't tell the story, or doesn't tell the entire story. Z effective only tells a portion of the story. Z effective tells the story for the elements in the same period. That's it. It doesn't tell the story for an element in the group, because there is a second factor, and we mentioned this, I mentioned this on Thursday. There is a second factor that comes into play when we're talking about a group. So even though the Z effective will steadily increase down the periodic table, why does these atomic size increase? What other factor comes into play? The answer is shielding. Think about an onion. Most of us have cut up an onion and looked at or think about a tree and the rings of a tree if you want. What happens when you add on more and more rings? It gets bigger. What happens when we add on more and more rings? It's going to get bigger. So, because we are adding on additional shells, atomic size increases due to shielding. So atomic size increases down a group due to the fact that you're adding on shells, which increases the shielding. So if we were simply to look at atomic size, it decreases across the periodic table and increases down a group. So how might you be asked a question on a test? It might be something like, place these elements in order of increasing size, and then I give you the elements, and let me just do some, because I haven't done this yet. Something like this. First thing I would do, folks, if I'm given this, is I'm going to assign the period. Period 3 for phosphorus, 2 for beryllium, cesium is in period 6, fluorine is in period 2, chlorine is in period 3. Can anybody tell me why I assigned the period number first?
It's like a higher period, then it'll increase.
Right. The shielding caused by the addition of the shells, that is more impactful than Z effective. So again, the shielding caused by the addition of shells has a greater impact on atomic size than does Z effective. So I went ahead and I did that. So if I want to do this in increasing size, that means I want the smallest listed first. All the way to the largest. And I know that cesium is going to be my largest. Now, the next ones in line will be the phosphorus compared to the chlorine because they are the next ones in the highest shell. So who is going to be larger, phosphorus or chlorine? Phosphorus will be larger because it is furthest to the left. Then chlorine. Finally, I come down to my period 2 elements, and who is going to be larger out of them? Beryllium, because it is the furthest left, and fluorine will be the smallest. So again, I used my rule of shielding first. The more shells that are in the atom, the bigger it's going to be. So I divided everything by shell. Then, if I have 2 elements or 3 elements in the same shell, the same period, then I use my knowledge of Z effective and how it increases across a period to understand that it's going to be smaller on the far right. Questions? Okay. So ionization energy is the energy required to remove an electron to make 1 mole of ion. So by definition, ionization energy is the energy required to remove 1 mole of electrons to make Why are you doing this to me? iPad. 1 mole of cation. So in other words, the chemical reaction would be X, which is just any elemental symbol up there. It's just a general variable for any element symbol up there. That element is going to become a positively charged ion with the removal of an electron. Now, what we can expect is that our ionization energy will decrease with an increase in atomic size. Ionization energy will decrease with an increase in atomic size. My favorite analogy to understand ionization energy is a household. And it's actually also my favorite analogy for understanding ion size. Let's say I'm a mother of 3, where the 3 children represent my electrons. Now, I personally was the type to do Girl Scouting, and I was at every band function, and I was at everything I could be, because I only had 1. But let's say I'm a mother of 3. I'm going to find it more difficult to do everything with every one of my children. I just don't have enough energy to do everything with every one of the children. So those children have a little bit more freedom to move about. And it's easier for those children to go running off down the street to play with friends. I might know where they are, but I'm not going to have as tight of a hold on them, right? The The same thing goes with our atomic size. You're talking about a really tiny atom. The hold that the nucleus is going to have on those electrons is quite stark. But as the atom gets larger and larger and larger, the nucleus just does not have enough energy to keep those electrons. And so those electrons are much easier to pop off and go running around. That's all ionization energy is. It's the energy for an electron to pop off and go running around. The bigger the atom, the easier it's going to be. Questions about ionization energy. So what would a question look like on a test? Place the following atoms in order of decreasing ionization energy. And let's see. Iodine, oxygen, rubidium, gallium, and carbon. In other words, folks, the first thing I'm going to do is determine atomic size, which we just had we just did. Because bigger atom, lower ionization energy. So iodine is in period 5, oxygen 2, rubidium 5, gallium is in period 4, and carbon is in period 2. And I want this from decreasing ionization energy, so I need the highest ionization energy to the lowest ionization energy, which means I need to put these in order of the smallest atom to the largest atom. Well, gallium's going to be in the middle, but I have 2 in the 5th energy level. So which one of those is going to be the biggest in the 5th energy level? Which one's going to be the biggest out of iodine and rubidium? Rubidium's the biggest because it is the furthest to the left. So rubidium is going to have rubidium is going to have the lowest ionization energy, followed by iodine, then gallium. Now, out of my other two atoms, oxygen and carbon, who's the biggest? Carbon. So it's going to have the next lowest. Keep doing silly things. Followed by oxygen. Questions? Okay, so if you look back, I know we talked about it. Group 1 makes a +1, group 2 makes a +2, silver makes a +1, zinc and cadmium make +2, gallium or aluminum, gallium, and indium make +3. In other words, they don't always just lose one electron. Loss of one electron produces a +1. So they don't always lose just one electron. Sometimes they'll lose 2 electrons. Sometimes they'll lose 3 electrons. So in other words, what we have is we have multiple ionization energies. The first ionization energy is the loss of the first electron. The second ionization energy is the loss of the second electron to make a +2. And the third ionization energy is the energy required to lose a third electron to make a +3. Now, to see the impact of each successive ionization energy, let's look at the Z effective for the formation of each ion in line. So you have your aluminum atom, and we could use the diagram on the left to help us figure it all out if we wanted to. We could go with the blue one first. And if we looked at the blue one first, then we would have, let's see, my S would equal 2 times 0.35 plus 8 times 0.85 plus 2 times 1. If you need to fill it in to see it, do so. So that means the S comes out to be equal to 9.5. So for my Z, which is, or my Z effective, I should say, which is Z minus S, that is equal to, aluminum is element 13 minus 9.5. You get 3.5 for the Z effective. Now, we are going to remove an electron, or let's say we take one electron and we pop it off. We remove that electron. So that it is completely gone from the structure. Now, if we look at this and do the Z effective, it would be S is equal to 1 times 0.35 plus 8 times 0.85 plus 2 times 1 or in other words, it's 9.15. So my Z effective is going to be 13 minus 9.15. So it is 3.85 now. We can come in and pop off the second electron, so that that one is now gone. Now, what we're looking at is we have S of 1 times 0. Sorry, 0 times 0.35. We don't have that anymore. We have 8 times 0.85 plus 2 times 1. Or in other words, it is now 8.8. So my Z effective is going to be 13 minus 8.8. So it's now 4.2. I can pop off that last electron. And now all those electrons are gone. So what we have is we are looking at just one of these electrons now as being our outermost electron left. So that means it's going to be an S of 7 times 0.35 plus 2 times 1. Which is 4.45. I'm sorry, you're right. It's not 2 times 1. It's 2 times 0.85. Which is 4.15. Make sure I keep that in right. So my Z effective is going to equal 13 minus 4.15. Which is 8.85. So let's talk about what you notice. What can we deduce about successive ionization energies? Okay. As you remove an electron, Z effective increases. Since Z effective increases, it is more difficult to remove the next electron because the atom or the nucleus is holding on tighter to the remaining electrons. What is one more thing that you can deduce about the successive ionization energies? You'll have to look at your sheet because I've rolled it up. There's a huge jump for this atom when you got to the third ionization energy. Looking at the periodic table, can you tell me why? Why at the third ionization energy are we going to see a monstrous jump?
Because up here it's going from like being in the third shell to the second.
Okay, I'm going from being in the third shell to the second. That is one piece of it. The periods are changing. Who else has the electron configuration 1s2, 2s2, 2p6? Huh? Neon. What is neon? A noble gas. So in other words, your noble gases have the highest Z effectives in their period. That means it's very, very, very difficult to remove another electron. So we see a dramatic jump in the Z effective when we get to the most stable form. You're going to see a huge jump in Z effective when you get to the most stable cation for the main group elements. Once you get those transition metals in, the reason transition metals can have so many different freaking charges is because of the Z effective not being quite the same. Now, what else can we deduce about the size of the cation compared to its neutral atomic size? Using Z effective. Z effective describes how strongly the electrons are pulled towards the nucleus. cations are smaller than neutral atoms. And what happens specifically as the cation charge increases? The Z effective increases, which means it's harder to remove an electron. Why? Because it's even smaller. So as cation charges increase, the size decreases further. So what we can say is a +3 is smaller than a +2, is smaller than a +1, is smaller than a neutral atom. For an isoelectronic series. And basically, this is a new definition. Isoelectronic is a series of atoms and ions that have the same number of electrons. Or they are the same element. Questions? Okay, so we talked about what it takes to make a cation. That is the ionization energy. So I just want to take a moment to sum up what we know so far for today. Atomic size decreases across a period due to increased Z effective. Atomic size increases down a group due to increased shielding, which comes from adding on more and more and more shells. Ionization energy is directly related to the atomic size. The bigger the atom, the bigger the atom, the lower the ionization energy. And that is simply because the bigger the atom, the less impact that nucleus is going to have on that outer electron. Now, when we talk about ionization energy, for every single electron removed, there is an ionization energy associated with that. The first ionization energy is going to be the energy needed to remove just one electron. The second ionization energy would be the energy needed to remove a second electron. The third ionization energy would be the energy needed to remove a third electron, and so on and so forth. Now, as we remove those electrons, the Z effective becomes bigger and bigger, meaning that as you remove those electrons, the size of the ion becomes smaller. And because the ion becomes smaller, it's much more difficult to remove that electron. It's kind of like sending these, I gave you the example of a family, me being the nucleus and my children being electrons. And if I have multiple children in my family, my time has to be spread across all the children. But as those children go off to college, I have more time to focus on who's left. And so I draw them in a little closer. And by the time that last electron's about ready to get off to college, I'm going to be in tears. Because that's like sending off that last electron. It's hard. It's very, very hard. And so I'm holding on with dear life, and it doesn't work. So, anyhow, electron affinity is the energy associated with making an anion. So, in other words, it's the energy required to add an electron to make an anion. Now, I'm not going to really spend a lot of time on electron affinity because other than to say, your non-metals that we know like to make anions, they give off energy when they make the anion. Whereas metals who don't like to make anions, they require energy to take on another electron. But I'm not really going to spend time on electron affinity because unlike ionization energy, there's not a specific trend that you can see. It's a little less obvious what the trend is. But what I am going to do is I am going to talk about the anion size. Does anybody want to guess what's going to happen to anion size? Well, let's just prove it to ourselves. Let's take oxygen, which is, and we're going to keep it simple, 1s2, 2s2, 2p4. And let's make O minus. And if we make O minus, that's going to be 1s2, 2s2, 2p5, because we've added an electron to make it a negatively charged ion. And then let's go in and make O2 minus, 1s2, 2s2, 2p6. If we look at our shielding, which I could draw out the structure, hopefully you're starting to see the trends here. The shielding constant for this is going to be 5 times 0.35 plus 2 times 0.85 and that's 3.45. So my Z effective is going to equal 8 minus 3.45, which is going to be 4.55. For oxygen minus 1 charge, that is going to give a shielding of 6 times 0.35 plus 2 times 0.85 which is 3.8. So my Z effective is going to equal 8 minus 3.8, which is 4.2. And then for oxide, my shielding constant is going to be 7 times 0.35 plus 2 times 0.85. Which is 4.15. So my Z effective is going to equal 8 minus 4.15, which is 3.85. So what can be said about the size of an anion compared to a neutral atom? Okay, so what we can say is as electrons are added, Z effective decreases. What is Z effective? Nuclear pull. So in other words, it means that the nucleus has a weaker pull on the electrons as anions are made. So our size increases with increasing negative charge due to a decrease in Z effective. So a neutral atom will be smaller than a -1 atom, will be smaller than a -2, will be smaller than a -3. So going back to our isoelectronic series, we combine these. A +3 is smaller than a +2, is smaller than a +1, is smaller than a neutral, is smaller than a -1, is smaller than a -2, is smaller than a -3. Questions about that? And we just proved why, because in large part due to the Z effectives. This ends our discussion on trends. So there are really, so let's talk about the trends. There was the atomic size. There was the ionization energy. There was the isoelectronic series. And there is, in a sense, Z effective for formation of cations and Z effective for the formation of anions. Questions? With only 5 minutes left, I'm not going to start getting into the ions and naming ions. We'll pick up with that after the exam on Thursday, so next Tuesday. Next Tuesday and Wednesday, next Tuesday. So this Thursday, we're doing a separations lab. Next Tuesday, we are doing, I will be lecturing on ions and getting into the polyatomic ions, and I will be passing out some things to help you remember your ions, because you'll have to start memorizing them immediately. And then we'll get into naming on Tuesday. By Wednesday, I should say, we'll get into naming. By Thursday. And then in lab on Thursday, we'll finish up any naming we need to do and get into Lewis dot structures. So I will see you on Thursday for the exam. And if you come by my office hours, Luna will be there, but I got to go pick her up around noon today.